I like this.
Tu prends pas le fait, tu peux pas prendre le
Oh, it's I didn't know this.
So good afternoon, everyone. Before I introduce the speaker, Professor Brown is going to say a few words.
So just appreciate everybody being here. This is part of our Institute of Optics Colloquium series. This is sort of one of those interim talks. It's fall break, but we're delighted that so many people are able to come out and participate in this. Looking forward to a great talk. This is also an important week in the life of the Institute. Our Industrial Associates meeting is later this week downtown at the Rochester Riverside Convention Center, as well as a wonderful conference. It comes here every 2 years. OptiFab is going on the next few days down at the Convention Center at the Rochester Riverside Convention Center. A lot of our industrial associates and other friends of the Institute are participating in that. So especially you students, if you do get a chance to get downtown, go to the exhibits and so forth. And I encourage you to do that. I'm going to hand it over to Jeanette to introduce our speaker.
Thank you so much. So it's funny, when I came, I've been out for a little while because I was sabbatical this year. So actually part of that has been kind of wonderful to meet some new colleagues in France. And Tom asked me if I was here. And I said, maybe I'm in a hologram, maybe I'm just just here. You may not be sure, that it's me. Okay, so, but anyway, with this, let me introduce Professor Jean-Louis de Bougrenet from the Department of Optics. He's actually head of the Department of Optics at the IMT Atlantique. IMT stands for Institute, Mines, and Telecom. And he's a specialist in composite liquid crystals, diffractive optics, and vision optics. He received many awards, including he's an Alexander von Humboldt Fellow, Churchill College Fellow, University of Cambridge, and Optica Fellow. He also has 65 patents. He's the founder of 6 companies, and he was a winner of the Cambridge Entrepreneurship in 2002, and the SPIE Technical Achievement Award in 2006. He got the Grand Prix laureate of the French Académie des Sciences in 2022, and is currently the CTO of a startup that is in Pittsburgh. It's called Cylensee, and he's designing and manufacturing cyborg contact lenses, as we're going to hear about, for vision uses in optics. Some of his deep interests are into vision restoration. So with this, Jean-Louis, I give you the floor.
Yes, thank you, Yannick. First of all, I would like to thank you for inviting me and offering the possibility to meet people and to discuss with some of you this morning. A very interesting discussion. I will be able to pursue that in the future. And I will try to speak about the title of my book, New Visual Assistant for Restored Visions. I will not restrict to restored vision, because I will address a broader topic, including augmented vision and cybernetic vision, which is, as you will see, is coming later. Of course, such kind of topic is very large and cover different aspects from the nano technologies to the neuroscience. So I will not just fly over this domain because they are very large and they will deserve a deeper development. So I will just give you some insight of all these aspects are interconnected. About the visual assistant, I just have to say that, in fact, this has been made possible by the convergence between different fields. The nanotechnology, the biotechnology, and neuroscience. There is a byproduct of what we call the NBIC domain, which is a very modern domain. And just as an introduction, I will show that is a long trend towards the making closer the information from the person. We start with the Macintosh. Macintosh was the first revolution for all people like me. It was a revolution in terms of ergonomics, and it continues then, of course, to improve this the access to the digital world with the laptop. Laptop was also something very useful. It was a very wearable material, so we could take it everywhere. And it continues with the smartphone because we have the same power, computing power on smartphones now that we had in the past in the laptop. And it continues with the introduction of augmented reality, but with the third party appearing here, which is the cybernetic world, the cloud in particular, because to this date, we have been connected, we say we are connected persons, and the role of the cloud increased a lot. And if I continue from the HoloLens, now the next step that has been pioneered by Google contact lens, but to say what we can put on the HoloLens helmet can be done on the direct with the contact lens. And if we continue, we can say that we can use cortical implant directly connects information to our cortical wave. So you see that this is a common trend, and it is in fact related to two strong levels. The first one, we need even more connectivity nowadays, and also even more mobility. So those are aspects when you look at this trends is that the eye and the perception plays a very particular role. I make closer the information to first the display and then the eye on the visual cortex. So the eye plays several important aspects that cover several important aspects as an emotion marker. Cognitive blood marker, stress and fatigue marker, but nowadays the eye can also be used as a sensor, biometric sensor, but also as an actuator. And you can consider that is nowadays the smartest brain interface. So, because over 70% of the sensory information transit by visual receptor. So as a reason why we focus on this very interesting analysis. Coming back to another aspect is not only the technology change the access to the information, but the representation of the world change a lot in parallel. At the beginning, we have the object, the world, the brain, and the eye. We watch the object, and the brain can see and interpret. Nowadays, it's a little bit more complicated, because we can offer in the last one a world with a superimposition of different information. We keep the access to the object to the world, but we superimpose to this world the creation of virtual object. This is the case when you use, for instance, augmented reality helmet, because we have artificial objects that appear in the action side. But we can have access to a menu, which also present on the field of view, which is a 2D pictures, which is superimposed. And of course, with, in that case, not only the brain, but something else, which is another brain, which is a cybersphere that will interfere with our brain. If you look at that, it is clear that when we will analyze the perception of the world, we'll have to switch between different. The eye motion will focus on different parts of what is proposed to the observer. So we have to switch into a virtual object, etc., etc. And we have a more complex operation on the eye motion, which is driven by the brain to manage this information. And generally, we will add intentional trigger because we can consider that not only we look, but we can interact on the world. We can interact, for instance, at the level of the eye by activating using the eye as actuators, for instance, by using the gaze direction or by the blink, so we can send message. But we can also interact with other sense, like the haptic actuations. It can be called to grab real object, but to grab virtual object is not the same thing to do because the brain will interpret differently what we do. And all these things will result, in some case, in a very cognitive overload. So we have to face very complex interpretation and interaction with the word, and we generate cognitive overload. What happens in this case? Generally, the brain protects itself. What it does, it will make what we call attentional tuning, that it will cancel part of the perception and we focus on specific tasks, right? To grab an object or to look at the menu. And of course, when it does that, there are part of the information which is missed because let's imagine that a danger will come in this area. If it were outside this tunneling effect, we never see nothing. It could be dangerous due to this mechanism. So it is necessary to restore a channel to bring information to the brain to say, be careful, you should shift and look outside. Basically, it is necessary to keep control, to recover the control, and to have some kind of attentional awareness. So it is useful. We should help the brain to restore this control. And it's the reason why that I place what you call the visual assistant at this level. We create a new element which will help the connection and to get rid of the congestion that would have at the brain level to interpret what is displayed in front of you. So there are various types of visual assistant. I've written IoT because generally they are connected to internet themselves. I will come back on this point. It's very important thing also. There are three main ways to create visual assistant. You have the contact lens at the cornea level, as I will discuss today, with the original concept of Google in 2009. You can have retinal implants, just background, at the level of the retina, as you can see with a mini solar panel, which will substitute to the self, this subretinal electric implant. And if we go further, we have all these nice objects which we plug into your optical cortex, visual cortex, sorry, using these nice electrical probes. Of course, the degree of intrusiveness is the same, from weak to very high. So today, I will just focus on this part, dealing with the less intrusive part and the more advanced in terms of technology. So the first elementary human-machine interface, because what we do, the visual assistance is to help and to create an interface between the brain and the outside world, is a contact lens. Why the contact lens? Because the contact lens will just be in the middle, will be a relay between this representation of the world and the brain. And the contact lens is just put it onto the eye, so that is linked to the eye motions, which is a very important thing. That is related to the eye motion. When the brain will send a oculomotor a signal, it will also act on the contact lens. So, and eye movements are a very important part of the vision action loop, in particular for the learning. So we are really at a crucial point of interaction to put the visual assistant. Just to illustrate what the role of the visual assistant would be, for instance, just to say, when information is depicted somewhere externally, let's say on the menu, for instance, thanks to the laureate, it will be necessary to control the gaze direction to display the information on the right retinal area. We have a discussion this morning with the team working on eye tracking. this is something that's very important to understand also how the perception works. And reversely is a way to measure where the attention is focused. When we have so complex thing, the overall system, if you know where the attention is focused, either on the real object or the menu or the virtual. So eye tracking is consequently one of the first elementary HMI that could be done, and I will try to explain how it is done on a contact lens, how it's implemented on a contact lens. So eye tracking, the first use of that will understand rapidly the interest of using the eye tracker. If you consider that this person, for instance, has a loss of the central vision caused by the scrotum, for instance, it is necessary to use the periphery, which is not dead. And so, if we have a consumption sheet which is displayed and grabbed by a camera, you should send the useful information at the right place of the retina, okay, independently for the eye motion, to be sure that the people will see something. And how it is done? It is done using a gaze positioning, of course, to display the information by eye tracking. We had discussions this morning about what is required to have a good eye tracker. I just indicate some features that are very important. We should not have any latency between the eye movement and detection, because we should establish a correspondence between what is displayed and for a given position of the eye, to be sure that we send at the right moment of information at the right place. Of course, to be immune to the lighting change, which is generally not the case with a standard eye tracker, because they are very dependent on the lighting conditions. The reason why generally they are used in an optometry box where we control the lighting. And also immune to microsaccade or other micro mode. Even if you consider it's interesting to measure this mechanism, putting the eye tracker on the contact lens will make it independent from motion, because you are directly related to the eye. And of course, immune to eyelid beating and eye escape, strategy of trying to escape what is discrete. So our idea was quite obvious to say that if we want to have a very good eye tracker, answering this question, the best way to do is to put it directly into the eye. To create the eye tracker on the eye. What we did with the first contact lens we called the Cyclops lens, is to introduce two lasers, to embed into the contact lens two laser pointers at the near infrared wavelengths, two laser, wide double, we explain why double laser. And you see the final device. We have the antenna which enable to communicate with another antenna which is set up into the eyewear, for instance, and communicate energy and data. And you have basic electronics and two laser DXL, which are connected and activated from remotely. So the activation and energy harvesting are obtained by magnetic coupling between the two coils, which is a standard technique so that there's no need to have battery. We can make a battery in the contact lens, there's no need for. So it was a very simple device. So just to say, and by the way, in fact, what we make, we materialize a laser beam. It's like if you put a normal director vector, just put it on the contact lens. When the lens moves, the normal move, and you just have to measure the duration of the lens. And we have, so when you have the contact lens, the second part is what we do with it, and is to measure the direction of the gaze. So we have several different ways to do. First, where you see the contact lens, which is put on a mock-up eye here. We have a world camera looking at it. So we using the beam splitter, we look at as a laser, as a marker. It is a fast camera. It means it's fast camera. Why? Because detecting two beams, two spots, is a very simple algorithm compared to eye tracker, which detect the pupils. They are making image processing, so the processing is not the same. It takes time. Sometimes it's a reason for latencies between when the object is detected and when the image is displayed, or a given amount of time, due to generally to the processing. So in that case, the processing is nothing. We just have to detect it to spot. And this is an option. So we can reach 200 hertz, for instance, repetition rate with such kind of device, and maybe more. So that we can measure very fast eye motions by this way. Another way is use a PSD. PSD is appropriate because PSD detects a spot position. So it's the right device for that. And we determine directly, we see the PSD is just in back. And so direct measurement, there is no computing. You extract the position of the spot immediately by the coordinates. Finally, we also included the contact lens in HoloLens 1 system. So that to display, to see the spot on the HoloLens display. I will give an illustration of that later on. We have realized a complete system to be wearable. For instance, you see one of the PhD students wearing one. We have done, you see, the eyewear, the headband, to put it on the head. And we, instead of developing a software, we use a common middleware using an existing eye tracker, at least the camera of the eye tracker, based here, and Raspberry Pi to compute the position of the direction of the. So you see the person wearing with the system, and of course in full mobility, we can, everything is on you. You can also it's different use of some eye trackers that impose a steady position. We test in a straight laboratory in Paris. It's an apartment which is devoted to make some tests for blind people. So with different lighting change, this is the test as currently done there. And just to summarize the interest of such kind of eye tracker, they are very robust, they are fast, okay, and also because differently from the image processing eye tracker, we can operate outdoors. We can operate outdoors because outdoors we have strong lighting change, and also with the sun. The sun is not very good for the eye tracker because they use infrared lightings, and the sun is a near infrared is a very strong source of near infrared, so it will in fact pollute the detection of and the detection of the. So this eye tracker is able to work outside with very changing lighting conditions. This is the reason why, in fact, the US Army was interested in to keep the SEALs and the infantrymen, because when they use a helmet like that, it is necessary, they need to know where the attention is focused on and to have a good estimate of the gaze direction of the soldier. And on the battlefield, you do not control the lighting condition and everything else. So it's a way to use a very robust system in this condition. Maybe it's not the best eye tracker in terms of accuracy, but it is the more robust, the simplest one. Because the basic idea is it's obvious to put the laser on the eye to detect the direction. Something is everybody could have the idea. It's not. So we test. We are quite advanced in this domain because we test. In fact, we are making regulation. We test this device first on animals, in particular on rabbits, to test a lot of biocompatibility test. And also on beta tester, I am here. I was the first to do it to show that they're not dangerous. And co-worker and PhD student, we agreed to test. I've seen that we discussed this morning that we have the same also. And we make a lot of preliminary tests dealing with the comfort in particular, because you should wear the contact lens during, the US Army said you should wear the contact lens during minimum 8 hours. So wearing the contact lens during 8 hours is something is not so obvious. We are ready to be sure that you are not irritation of eye, etc. And just to show you, I will short video to show you how it looks like when you put the contact lens on the eye. And now we are currently making a clinical test on a clinical sample. They are in progress both at the Vision Institute in Paris and Pittsburgh. I remember the reason why I'm here, because I start working with José Sael, who was the head of the Institute of Vision in Paris, and we know he's the head of the big Vision Institute in Pittsburgh. And he told me to come in Pittsburgh to say, come here because to work is a very nice place to work. So it's the reason why I created my subsidiary. It's in Pittsburgh, Cylensee, to work with Jose. I'm based at UPMC at the moment. And of course, Pittsburgh is very close to Rochester. So you imagine the possibility of interactions that are offered for us. Just as a short description to see that. I will launch the video. I hope it works. Yeah, we start with the slit lamp measurement to test the clearance of the lens. And also we test on the quality of the lacrimal layer to get rid of eye dryness when you keep the lens a long time. And the contact lens is a scleral contact lens. It is very steady, it doesn't move on the eye. It's rigid contact lens covering the sclera, so that when you put it, it's customized to your cornea, and you put it, it doesn't move anymore. Of course, for eye tracker, it's important that the sensor doesn't move when you blink or something like that. And you see that there is no effect. The lacrimal layer also is so. What's the first stage? Yeah.
How comfortable was the contact lens? I'm curious. Since
When it is customized to your eye, okay, it's very comfortable. So it's not easy to put it. Yeah, it's not like a soft contact lens. But after that, when you make experiment, we wear the contact lens more than one hour, sometimes 2 hours. Scleral contact lenses are very comfortable and very steady. You don't have to balance it. You don't have to balance the effect. When you have soft contact lens, when you blink, you realign. In fact, the non-align. It's really customized. In fact, we analyze the surface of the cornea, and we design the inner surface of the contact lens to your own cornea to align the contact lens correctly.
there was a custom lens for each person of the each of the
like you have a refractive correction. Sometimes you can add a refractive correction. What I do is I keep the pupil free, so it's clear that I'm just concerned by the sclera and it's not the central tissue. It's compatible with people. We have a refractive correction. So, but for us, making the eye tracker is nice for optical scientists like us. But the next step, of course, is to go beyond the eye tracking and to incorporate optics inside. So the idea is not new. People try to make a telescopic system to really address the right position, also to magnify picture which are displayed on the display here. This is a standard idea. The idea to introduce that in the contact lens and see something like that. We did it. So the first thing was to introduce in the contact lens a first holographic element. holographic element that have been computed with all the facilities we have. First we computed the device, and we realize the pattern on the glass plate, we cut it, and before embedding it, we have to design the spacer on which we put the contact lens to be at the focal distance of the laser. And the way top alignment, because the focal length is very small, is few hundred micrometers. So, and when we assemble both devices, it has been added to the laser, and you see the hologram which has been incorporated inside. And why we did that? We did that because, for instance, if we want to use the laser pointer, to use it with a PSD, we have to collimate the laser beam because the laser beam will expand, that's a far-out function. So it's necessary to introduce a collimating optics to maintain a very thin beam and to detect it on the PSD. So it was first requirement to control the beam divergence. But if you do a collimating element, we can do anything else. For instance, what we did, we realized the Fourier hologram of a cross. So it's not collimating lens, we create holographic Fourier element that we implemented at this place. You see here the eyewear with the world camera inside. And what we did, we create we project the pattern of the Fourier holograms at a given distance so that we can project across, illuminating a board like it's here, a board with several picture icons. And what you see here is what the camera sees, because the camera can detect infrared wavelength that we cannot detect, so the user doesn't see the cross, so that it works independently, but the Big Brother system sees the cross. First, it can analyze the cognitive, in fact, the attention of the user, and also analyze all this movement. We give an order. Okay, I designate the targets, look at it. I have to be sure that you identify it and you designate it, and the overall system controls that. So it was interesting also for the US Army to use it in the helmet to be able, with adding the entry, to designate a target and to validate an instruction. So once again, I have a short illustration we understand. So in that case, we did more than eye tracking because it's possible to know where the attention is focused because we analyze across whatever we use to assess the cognitive load. We follow the trajectory. We record the trajectory of the people. When I give an order, I can follow where it's going. And also to activate the function, because it's a way to activate functions, because the system can detect the cross, where is the cross, and establish a correspondence to the cross and a display. I will give an illustration later on. So just look at the video. So you will see, and we act first, you see in front of you the eyewear, the one camera, and the contact lens with the light. The spot is one of the pixels has been activated, and the lens with the contact lens we turn on. We see best ways to activate the video, and you will understand. We switch off. We switch on. We see two lasers. We rotate, and we see what is observed on the board. Yeah. Of course, the hologram is not perfect, but we can improve that. It's not a technical issue. It's not something simple. But we realize a very important function, establishing a connection between the eye giving an order, the eye designating something, the eye validating something. You know, it's the first step. The interface is bilateral. We can receive information, but send information back. It's a very important function. But for us, it was also something interesting, but not so interesting. We can go further. The next step is what we name parafoveal retinal augmented reality. We understand what it means. If I can project a pattern on a screen, I can project this pattern on the retina. I just have to fold the objects. And now, when I do that, I am very close to something that you know with an augmented reality helmet, but not on the helmet, on a contact. So what we did is to start first with a limited number of icons displayed to understand how it works. So the part on the telescopic light guide, which enables the projection of symbols retina. The light guide is there. That's scale 2.21. You have a guide, another guide with at the limit of the pupil. You can see that this is the pupil. You can see you have an hologram here, just here, and magnify it just here. And this hologram is activated by a laser. The laser beam is magnified by the guide and will illuminate the hologram, which is a reflective hologram, which will project the pattern at the right location on the retina, onto the retina. Yeah? So I activate remotely the laser, which displays the information on the periphery of the fovea, which is the case. And I can use several holograms like this. So it's something that is very similar to that. Or if you have a car, you use head-up display. So you are driving by nothing in front of your direction side, but in the periphery, you have a lot of information, giving information about the status of the car or whatever that are displayed in the periphery. Here you see the biker. The biker can bring something like that, giving information warnings, but also information about biological sensor warning. So it's something is rather HUD than a pure augmented reality contact. But it's the first step toward a full augmented reality contact lens. The very important thing is that because maybe you know the company Mojo Vision, we have heard about Mojo Vision probably. Mojo Vision try to do the same thing, but by putting a display directly in the middle of the pupil, just in front of the display. If you discuss, say that to ophthalmologists, generally they don't like that. They don't like to have something really in front of you, for many reasons that can be understood. First, because we reduce the quality of the pictures, but also in case of a breakdown, maybe you can read the device can be opaque, and in that case we are blind. So it's some situations that you cannot accept, and the reason why in all the device, and you will see also later on that for some healthcare treatment is very important, but all device must keep the pupil. Means that the information is generally projected from the pupil area. From the pupil area, sorry. So we have realized the first demonstrator before. Yeah.
Yeah. So I was just curious, how far into the periphery are you actually projecting the?
Everywhere.
Because like I was just looking at that image that you had up.
The previous one?
Yeah. Yeah, the one with the biker. And like even at this distance, if I focus my attention on the center of that image, I can't really read the information on the side. So I was wondering, like, is it like, how do you know where the optimal region on the retina is?
I will explain. You have an attentional region, okay? The retina acts operate differently. If you are on the parafoveal macula, different response for the cognitive brain that will react differently. So we will see that, as you say, the location where we project that is very important. Just to say, if I'm a biker, because when you drive ride like that, I ride quickly, I see the road, but I notice information. I'm able to recognize some very simple icons. Is that warning, for instance? I don't have to move the eye. I understand that the brain is able to understand, to detect limited number of signals that can be interpreted very easily without disturbing the main observation of the world. So, but the location is very important. We come back on this point when I will deal with the treatment of, for instance, or presbyopia or myopia. So we realize the first setup at scale to 1 by emulating everything, but just you see the annular ring. We emulate the cornea, the pressure line, etc. And we put a camera on the backside. It's a scale 2 just to see what happened. And we see that on the video what the wearer should see. Right? The system will signal, for instance, arrival of some dangers that he cannot see in his fog, for instance, because it's hidden. It will send a danger signal, for instance, with something flashing with a color. I'm able to detect something happen, it's sufficient. And so the pedestrian is about to cross the road, and the signal is appear when the president, you see the signal appear and disappear. Once again. Okay. So now I will try to give an explanation to answer to the question. I will focus because it's before being able to make pure augmented reality contact lens system, we take time. Because technologically it's not obvious, and most of vision stopped the work because the leap was very high to do that. But it will be done in the future, but it's too early. And we focus on healthcare application because there's a very interesting use of this system to treat some retinopathies and general disease of vision impairments. So I will focus on that. And before that, I will just give some figure with the cortesis of Optica, which is a big company making glasses in the world, to give you some give an idea of what are the main concerns nowadays. Of course, you know that in the world, people are not the same opportunity to get just spectacle. It's clear. But what is interesting is to also to anticipate the future healthcare issue. And of course, there are 3. This one we know because everybody is concerned by that. I will not address that because we are responsible for our own disease. Okay? But the other one is more complicated. One is due to the aging, with the presbyopia, and everybody is concerned by that. I'm concerned, but everyone after when we become old. And the most important one is the myopia. Myopia is a big issue, is a big concern nowadays because it concerns a very young person. So I will focus on these 2 big issues. I will try to show how the contact lens can be helpful for treating the presbyopia and myopia. And you will understand maybe why, in which area I will put the one. So the first case is macular degeneration. So the most obvious case is that we have this black hole in the central vision. And of course, is a big handicap in the everyday life to get that if you try to read. So there are many ways to bypass that. You can restore it. Restore it generally is surgical intervention, but you can also rehabilitate. You can train. There are many ways to bypass. It depends, of course, of the degree of your hand. I will just give illustration. AMD, there are two main cases of AMD. The first one is age-related macular degeneration, as I told you, is concerned everywhere. But there's also some genetic origin, neuropathy, which is genetic, which is called retinitis pigmentosa. The interesting case that in fact they destroy the retina. For them, there is a central vision, so where central vision is concerned rapidly, and the retinitis pigmentosa is start from outside, from the periphery, and grow to the central vision. So they are both are reverse. And of course, the smart contact lens can be useful in both cases. In the first case of retinitis pigmentosa, we will send a signal in the eye which is damaged with a given wavelength and a given intensity, so that it is detected not necessarily by the first layer of the cell, but by the ganglion layers. So, it's a way to stimulate just by sending warnings, for instance, important information, and stimulate this part which is damaged. So it is help also people to navigate, because I send arrows saying that you have to go right, up, down, etc. I can send information. I will explain how this information is coming from afterwards. And also another more conventional aspect is to help people to understand all their peripheral retinal locus is a way to use, when the central part is damaged, the periphery is not damaged, to train people to move their eye so that they align the external vision with the part which is not damaged. It's a training, it's a way to help people doing that currently without thinking about it. It becomes a reflex. Huh? And also to test people to best use their peripheral vision. We have seen something this morning also which is similar, so that people have the contact lens. The contact lens we display across on the screen. The people will be able to look where it's looking at. And we say, you have a target, you have to move your eye to superimpose the spot with the target. So he can train directly himself at home. He can train his PRL easily at home without being able to see an optometrist or an ophthalmologist. It's something that can be done easily. So the retinal, 2 words about the retinal restoration. The way I'm here in Pittsburgh, because José Sael is well known for working on this, which is head of the Vision Institute in Pittsburgh. The restoration is a very, very ambitious thing, because we really change what is damaged, replace. Okay? It's also for startups, is a very interesting added value business, because it's very expensive. So there are two different ways to do. The first way, as I said before, is to put an implant, a subretinal implant. Generally is a photosensitive implant that we in fact activate the optical nerves. We replace the dead cell, and we restore with not the same resolution, with the degraded resolution, but when you are blind, to be able to perceive something is already something very, very, very good, yeah? Very, very nice. So these systems are implemented, and you see, you put this device here, you see it, just the retina. And there are companies doing that. But generally, it is accompanied by the helmet, because you have to project something is coming from the helmet, yeah, and will be projected at the right place. If I project outside, there is a nonsense. But it is moderately intrusive, because you have some chirurgical intervention. There is another option, which is optogenetic. Optogenetic is less intrusive, because what we do, we encode a protein that will be, in fact, added to the ganglion, and compared to the ganglion, we are not photosensitive, but photosensitivity. So that the cells are dead, but the ganglion, which are not photosensitive, becomes photosensitive to a given wavelength, generally amber. Okay, so it's a way, it's weakly intrusive because it's a treatment. But in that case, I like for this situation, it is necessary because the ganglion are a particularity that they are around the optical nerves. So it's not something the cells are distributed regularly, but the ganglion not. You have something where we have to adapt to project the information on the corona because the ganglion follow a corona shape. So it is necessary to introduce a specific optics to project the information at the right place. So in both cases, this device will need a visual assistant to be sure that the treatment is really efficient. If I move the moisture without any control, of course, the result will be not satisfying. So generally, they are connected. This will introduce the big brother now at this level. In fact, it is connected to cognitive eye. So we have a system that will operate and will organize, display the information at the right place. It's not the main body that is doing that. So generally using a smartphone, etc. So it's the reason why that the key of cycle, as I said, is you have to stimulate precisely the retina free of any eye movement and blink. When I blink, I shut down. Okay? It means that with this system, I can continue to see something with a closed eye. Okay? And the contact lens will play this role either to make eye tracking or to project directly information on the. So it's the first use of the visual assistant for as a support of this restoration surgical intervention. But now I said the wolf is in the house. It is clear that the connection with the cloud is directly done by smartphone. One possible input. So it's interesting because I have access to very useful information. First of all, I can localize myself in the surrounding. So if I have a smartphone, I'm able to be geolocalized. But I can also get knowledge about the surrounding. If I use Google Maps, for instance, I can know, I anticipate some crash because Google Maps can detect people cars are arriving with possibility get a crash. So the information is coming from outside. I can myself, with my small brain, be able to say there is a crash possibility. It's coming, the information is coming from the cyber side. And also to communicate warning. The basic idea is that I can communicate warning to the people. Now you look at your smartphone, it's too late. I look at smartphone, I have no time to react. The information is directly sent to the eye without interfacing through the smartphone. And this can be done for all the three cases. You see here, the contact lens has this small circuit with a transceiver, with what you call NFC transceiver, that will communicate data with smartphone, with a link or near field connection, with a near short distance. It will communicate information from that smartphone to the contact lens. You get everything, warning, but everything else. I can do the same thing with electronics. I can say, I can display the real world to blind people, but I can display different things. Virtual world. It's the same. Yeah? And of course, with cortical implant, the same. When you have electrode somewhere, we have a connection like that, you can have a link with the upper level, which is science. There is a positive aspect. And it's used like that because we can have a way for blind people, to make some obstacle avoidance because we can detect obstacle and say people in front of you will share and send warning saying go to the left. to get. But more than that, we can also guide people navigation within the building. It has been done by UCLA using vocal, oral, what's called information. But of course, vocal information takes time because we have to interpret. It's better to do it visually. You send an information visually, you can really make navigation easily by sending information directly on the eye. Just with arrow, up, down, right, left. It's enough. So this is the best aspect. But there is a dark, also the dark side that you can imagine. I can send a lot of other things coming from the internet with the purpose to make money, to sell a lot of things. But this is a common situation for a scientist that when you do something, there's a bad and aspect. So basically, it's a very interesting candidate for obstacle avoidance, and it will help people to move outside by this help of geolocalization, for instance, using this kind of visual interface. So I go to enter into the main issue, the main concern, which is the main, as was considered, the myopia. So just a figure, we come back on the picture because it's well known, but it's interesting to see also the situation in the world. I was surprised by this figure because I consider this stand is well known in Asia for many reasons, but also USA is concerned by that. Reason one in Pittsburgh, I found people to make a clinical test, but it is really a world concern also for advanced countries like USA. The causes are multiple. There are genetic predisposition, but also the fact that people don't spend a lot of time outside, outdoor, and they are near work exposition by working in front of the TV, where there is kids in front of the TV, and then in front of the PC, and then in front of the smartphone. All these causes converge to the same result. So it's a very important main concern for people making glasses and also for the community. What will be the role of the visual assistant in this plan? It's just a small part, but already I want to show you some illustration. First of all, it's very simple things. It's the mitochondrial stimulation. Mitochondria is really the cell which produce energy for the creation or production of cells. It's a very important element in the life. So you have to stimulate the mitochondrial stimulation of the tissue, of the retinal tissue, the choroidal tissue in particular. And so recent research shows that increase the blood flow and axial elongation of the children will be reduced. So there is an effect that is some people use, for instance, current exposure to a torch during the day, limited amount of time. We put a torch in front of the eye and we stimulate, we illuminate your eye at a given wavelength, because this wavelength is the mitochondria sensitive to this wavelength. So the mitochondria will transform a wavelength into energy. But you see the picture, if you try to do that during the day, it's not very convenient. Other solution use glasses with also a lens. And what you propose to do is to do the same, but incorporating into the contact lens the source. You see it? So in that case, we don't need to have hologram. You have, in contrast, to create a very uniform projection of this wavelength on the retina and to control this first, the lighting balance. When you do that, we don't know exactly what is the light distribution of the retina. I can't drop nothing in fact. Okay. By the way, we are able first to have a quite uniform lighting of the retina. In that case, I just need 3 LEDs to obtain a very uniform lighting of the retina. But what we do more is that we are able to have better control of diffractive, but better control of luminance, because I can control the level, the repetition rate, the frequency of exposure, and the duty cycle. So, you know, the length of the exposure time within a period. And to start the process remotely. I can decide, I am on smartphone, will determine at which time, at what time I should start the process. And I keep the central vision free. I maintain, I'm not in danger, because I continue to see. Of course, I should not bloom and smear the retina, but I continue to see the outside world within the treatment, during the treatment. Okay? And of course, it is independent from blink and eye motions. So once again, I have a short illustration of that. So well, we see the device is very simple. We have, in the first case, we have seeing a laser, we have LED, I have 3 LED. I have an NXP transceiver. The transceiver, we switch the LED remotely and determine the exposure time and the exposure power. So the lenses, the eyewear has been simplified, of course, and we can include a refractive correction. And you will see here the experiment is done. I put the antenna underneath a sheet and just move the contact lens. And because the field value change, I will activate the consequently the lighting of the LED. You see it. When the lens comes closer to the sheet, it lights, and when I'm far, it switches. Okay? Such kind of device, as I said, is very important because generally it concerns pre-myopia of kids or children. And when you do that, the mother or the father should be there to be sure that the kids will really follow the treatment. And by this way, it's not necessary to have someone driving the treatment, but we can start the treatment from your smartphone. We determine what time I start, I can operate different ways and without disturbing the different line. So now I will develop more. So the second aspect, and sorry, a friend is the second aspect is it concerns something which has been also demonstrated to slow down, slowing down the myopia, is in fact what we call the defocus, which is defocus, which creates changes the choroid thickness of the tissue. So the myopia will be. There are two aspects which are important to understand. There is a mechanism that will change the thickness of this choroidal tissue. If I stimulate in this area, it will swell, and of course, we stretch the back part, okay? But it will depend on the size of the defocus. If it is myopic or hypermyopic. So, and the most curious thing is that the brain is able to detect the sign and magnitude of this. So because we are in the part of the retina, which is the attentional part, which is the brain operates differently. It answer one question that depends where you are, and the neural network don't do the same thing. Where depending on the part of the retina, so there are different behavior, and the myopic defocus enable to slow down this change of in the eyeball. How it is done is very easy to understand. So it is done by introducing in the periphery. Yeah, we are introducing in the periphery correction. In fact, we create a defocus in the periphery. And very important condition that we should not interfere with the central vision. Both effects are decorated and should be decorated for the central vision. And by creating this defocus, when we wear the ears contact, the brain will try to remove the blur and play on this choroidal tissue, to change the thickness and then to strengthen the legs. Of course, if you do that on the lens, on the spectacle, when I move the eye, it changes a lot because I should have the fixation in the center, because to be correctly applied, you see, it could be symmetrical, and this projection should be done on the periphery. The basic idea is to say, instead of doing that on the spectacle, I do that on a contact lens, which is the same. So it's a work which has been carried on by a team, a US team with Kubota, which is an American Japanese company, and a team at the optometric school in New York. That they test of the impact of this myopic defocus on the correction and the reduction on slowing down the myopia. What we intend to do here is to say, in fact, the blur is a way to operate to reduce the blur. But because the part of the retina which is concerned is an attentional part, and the cognitive aspect is also another important parameter. So if we can add to a blur the projection of picture icons in this area, we think it will speed up the slowdown of the myopia. So the combination, combining in fact blur and the projection at a given wavelength of cognitive symbol will be beneficial and will improve make faster and more efficient the axial elongation stabilization. So it is what we will be done, for instance, when we concern the size scale 1 of the prototype, is scale 1. So the hologram will be implemented 8 holograms there and will be activated externally to project the icon at the right place, blur on blur. So just because I have to stop.
Yeah.
Okay. Just to say what we are doing at the moment is making that. We are doing that, and there are many issues, including in the contact lens holographic element to project at a given wavelength, at the given location of the retina, the right image is something that imposes in an optical viewpoint to be able to control 3 things. First, you should have a very acute modeling of the eye, because you see the size of the optics is just here, very small, and we should project at a very precise location of the retina through the optical system. So it's necessary to have a good model. The second part is to be able to build, and we have a discussion this morning, so these optical blocks, which is very small, you see the size, including a source, a light pipe, holographic elements. You see the size. It's very small. We have done an idea of the light pipe size. We are able to make holographic elements or metal lens. That's we are working here to be able to make the best optics to project to make a good imaging on the retina. And the last, of course, to be able to encapsulate that in a contact lens. You can see this is the cross section here of the edge of the inner diaphragm and the outer diaphragm. You see all this part has been lated by a lating machine, and you see the layout, the source, and the DOD which has been included in this part. So we have a volume which is limited. We should consider that the volume constraint is very strong to put everything inside. And all these three aspects are strongly linked together. I think I will finish. So I want to go through that. Now, the facilities also were discussed. Just to conclude, to say that in fact, we consider is the reason why we're here to discuss with University of Churchill College is to say that in fact, the development of active when you include source inside of smart contact lens impose a very challenging miniaturization task to make intraocular optical system, which require very precise alignment to address a very specific part of the retina. And it is also an ideal platform for testing optical metasurface because of the volume constraints, all these optics are very thin. We can have several optics. We should have a very thin optic. So we combine in one optics a lot of optical features like large numerical aperture, off-axis lens, etc. So it is a good way to test the metasurfaces. So we have three potential collaboration topics. First, myopia treatment is really to see if projecting structural content at 670 nanometers could help to speed up the myopia slowdown by combined to defocusing optics. This is the first thing. In collaboration with the PMC at Pittsburgh and us to miniaturize optics, make a design, as we say, and also testing the lenses. And finally, we have also another more technical optical issue, which is when you make this optical element, they are so small that we have to, the assembling become very important. And the design assembling to reduce the tolerance issue. When we make a mistake on one, it is important directly on the retina because we don't reach the part which is of interest. So on this aspect, because this is kind of smart visual assistant, open a lot of possibility covering healthcare domain, optical science, and also design of methods. And just to finish, for people who knows this whole series, Stephen was a $6 million man, and he had a bionic lens. Just to say that, in fact, nowadays, it's no longer such mission. We are very close to that, and worse than that, because he didn't know internet at that time. And no, it's worse than that because we have a connection with internet. Okay, thank you very much.
We have time for one question. I know it's getting really late for some of you. I know you have some of your children have to go pick up and things like that. So, any pressing questions? I know we're going to continue the conversation over. Perhaps Susanna. Yeah, go ahead.
So with the retina implantation, right? How do they often? And so in one of the slides you mentioned that one way to fix the retina, like the holes, the impaired building, and like ionic implantation, the retina, right? But the thing is, like, do these degrade in time? I assume, like, do you need to replace it?
Oh, good. You know, that is. We depend which kind of with the first one with
The genetic one, the other one, the one actually surgically.
Yeah, this one. In fact, this the RFID connection, you could outside, for instance, the external circuit, and it will communicate by magnetic field. Then through the circuit, which is just on the eyeball, just outside the eyeball. It's surgical. We have surgical with that. Maybe to be sure that I answer your question. There's one slide. Which one? What one of these?
So yeah, with the eyeballs, you do, like, yeah, one when you actually have to go down.
You see an example.
So the one right by it, right? Where they have to like actually put the graphene or like things. They on the retina, they have to like actually put the array of like replacement.
Yeah.
So I guess my question is like, do they go bad in time? Do they have to replace?
Yeah.
Okay.
Okay, one more question and then I know.
I apologize that this is a little outside of the scope, but whenever I hear we talk about AR
Mhm.
and we talk about the problem of figuring out where the eye tracking and where the eye is focused. One thing that I've never heard brought up is this idea of inattentional blindness, which is more of a psychological phenomenon, right? Where you could have the eye focusing on something, but that doesn't necessarily guarantee that the perception of the person looking is actually registering what's going on there, right? So how is that, how do you guys approach that idea? And is that something that's being, is it kind of like
It's a support of the supervising system that do that for you. You substitute, I have something, for instance, when I say Google Map is looking at the surrounding of you, Google Map will analyze the situation.
So let's say, for example, one area that I know psychologists have hypothesized that intentional blindness comes into play is like motorcycle vehicle accidents. So there's this common thing that even though the motorcycle is coming head on or to the side of the driver says, "I never saw it."
Yeah.
Right? And one hypothesized explanation for this is this phenomenon where you could, visually you're seeing there's input, but perceptually you're not registering. So
Is a way
how do you
to
tackle that issue if you're just, we're talking about trying to, incorporate what someone's looking at and, figure out.
it's some kind of augmented vision because you bring something else that you, as you say, first maybe you can see or your attention is not focused on. Something supervises the situation for you. It helps you to get rid of that. But for instance, I'm walking in the street, there is a corner street, and someone is coming. I cannot see it, but Google Map sees it.
Mhm.
And Google Map can transfer the information to you. So it's a way, but it opened a very, I don't know, from car crash, it's also to anticipate what you say, or maybe to anticipate the situation. Internet can compute. Maybe he knows the speed. He can say, okay, there's potential crash because you anticipate the trajectory.
I get that. I guess I'm just using that crash as an example of the computer registers that this object is in focus and nominally the person is seeing that object. But perceptually, the person, even though the eye is focused on that object, they're not actually perceptually registering that.
Mhm.
Right. So how is that tackled in the AR? Or is that
No, it was the case with the US Army because when people on battlefield operation, because they are channeling on those things, a lot of information, they focus. So sometimes they focus on the target, don't see a moving object coming towards us. So the overall system camera detect it and send a warning. Send a stronger information, stronger stimulation with a particular color. And also with a frequency. The frequency is not chosen. It's really you should choose the best frequency to do that to make the people aware of the danger. But you should add because, as you say, you have attentional tunneling. It is a question. Attentional tunneling is the first step. But more than that, I can anticipate also a crash or something like that because it is the same. I have supervision system, and in some way it's way I make augmented body because myself I can't do it because I don't see it or because my attention is focused on something, and I have a supervision system that make it for me. This is a benefit of using some kind of device.
Is there an idea of queuing in maybe additional redundancy, like an audio signal?
Yeah, of course, because also we combine with also detection. but it's managed by I assistant that manage that overall. I'm the end, the cyborg lens is at the end of the process. It's just how the device will act, send information. But to be sure that I see it, because I can escape, and I cannot escape. Look, I turn the eye, it displayed. I blink, it displayed. There is no way to get it outside.
Okay.
If we have to, like, I just have one interest follow to that. Sorry, I know, like, there's this phenomenon that happens. I don't know if there's a name for it, but
There's a road type of
if you have like
diagnosis. Road diagnosis, I think, like you are driving and then you are going, but like you are looking, but you don't see road diagnosis.
road hypnosis.
The attention is somewhere else.
Yeah.
Even in a system where, let's say, you have a warning popping up on your phone. The one thing I know from, like, from building, worrying about interlocks and redundancies and safety is people tend to, when they become normalized to a warning symbol, they tend to not pay attention to it as
I change the symbol. I change the symbol as a capability to change symbols, same the repetition rate. Yeah, there are many features. You can turn many features. It's not a simple display. Yeah, if
that's fair. That's fair. I know it's more of a UI.
the brain is trained to everything. The brain can learn and I agree with
That's a good question.
No, but it's just an additional information that, and for people who have impairment, it's better because they don't see nothing. So yes, two level people like you, metropic people, so it's augmented vision, and you can say that. But for people with which are impaired, is for them it's something they see something, because.
Well, let's thank our speaker again. Donc, Kevin, vous pouvez m'attendre, il a paqué, c'est ça? Et vous m'attendez dehors, là, moi, je suis remontée chercher ma feuille, je suis redescendue tout de suite. Et Susanna va venir avec nous aussi. Hein? Because I'm going to drive, Maybe I can park in front of the CBS, maybe tonight, We'll try, but otherwise I'd drop you and I'll go parking in the other one.
I think generally.
Yeah.
Just take two or.
Yeah, I will do that. We'll be four of us, we'll see what happens. But if not, I'll go around and go park somewhere else and I can help you guys so you can go get going.
Okay, but I mean, hopefully we'll.
Yeah, I'll come right back.
Yeah.
Nice to meet you.
I think we have a common, Pablo.
Oh, Pablo. And yeah, Vincent.
Il y a la
Oui.
je suis sûr, au Pablo, non, c'est Roberto. Pablo.
Yeah, Pablo was actually my. Yeah, so that's why they're not sending. Okay, so you're based in France? Okay. Okay.
I didn't realize I can speak long time about. And
Yeah, it's interesting that you mentioned motor vision. There is another company where in fact also develop contact lenses with smart contact lenses.